I recently adjusted my audio, so hopefully I'm not too loud here. I'm gonna lower it to -3 decibels, and I'm actually gonna go pop on the stream and see. Let's see here. Maybe if I do a recording, yeah, let's start that. I'm gonna start a recording. Test the audio levels, see if this is too high. Stop the recording. Alright, and I need to switch my display here. Sorry about this. I just realized that the changes I made to the audio levels might be blowing out the mic. And I don't want that. So let's see. Yeah, let's start that. I'm going to start a recording. Test the audio levels, see if this is too high. Okay, I think that is reasonable. One thing I did notice is that the audio levels were too low previously on previous streams and videos that I recorded, so I increased it, but then I did one recording for a friend that the audio is just blown way out. So hopefully this is an improvement. Alright, it is Thursday. This is the we're going on, I think, 2 weeks now after, what's today's date? Well, not really. I wanted to have this book wrapped up by the end of January, and it's first week of February. And now we're a week past when we wanted to finish it originally. But, you know, that's life. Sometimes things just take longer than you expect. I was going really hard the previous weeks, reading 100 pages a day, learning a lot, but also not really writing a lot of software, like a lot of code. So I already got a makefile in this directory, so I'm gonna try to do more experimentation as we read this chapter. I'm excited for this chapter. This is one of the better chapters of the book I've been anticipating. 61 and 63 are the two chapters I've been really anticipating, so let's get into it. All right, this chapter considers a range of more advanced topics relating to socket programming, including the following: the circumstances in which partial reads and partial writes can occur on stream sockets. Yeah, I mean, stream sockets are bytes, streams of bytes. So you can get a partial read of a message that's encoded in that stream. Because it's not a datagram or a how would you say, a messaging socket. It is a stream of bytes, similar to anything, any of the built-in Unix mechanisms like pipes or file descriptors or really anything in Unix that's a stream of bytes. You can have partial reads and partial writes, of course. That's why read and write return the amount of bytes that were read or written. I guess this goes into some of those situations. The use of shutdown to close one half of a bidirectional channel between two connected sockets. Trying to think why that might be helpful. I cannot think of, other than just like ensuring one end cannot send or receive. I don't see how that is helpful. Maybe it might reduce resource usage on the server, maybe. But yeah, I can't see how that would be a performance or a huge performance benefit, other than just having this correct semantics that you want. The receive and send IO syscalls, which provides socket-specific functionality not available with read and write. Okay. The send file system call, which is used in certain circumstances to efficiently output data to sockets. So this is where you have a file descriptor for a file and another file descriptor for a socket, and you hand those file descriptors to the kernel, and you say, hey, take all the data that's in that file and send it straight to the socket. And you don't have to involve the user space at all. And my understanding is that this then became more general in the form of splice, which we saw a couple streams ago. We've encountered it a couple times now, which is a more general form that uses pipes instead of sockets. But you can use if one end has to be a pipe and the other end can be anything, like a socket, a file, whatever, doesn't matter. So it's a little bit more general than send file. But from what I understand, it might not be as popular as send file in adoption. Details of the operation of the TCP protocol, with the aim of eliminating some common misunderstandings that lead to mistakes when writing programs that use TCP sockets. The use of netstat and TCP dump commands for monitoring and debugging applications that use sockets. Okay, TCP dump is still a thing for capturing packets. Netstat is not. I guess it is. Netstat TAP. Is it netstat? No, it's not netstat. What is the command that you use TAP for? My brain is not pulling it up. One thing I'm noticing is that my terminal captured that. Interesting. I'm just gonna exit this terminal. I might just tear down everything because it looks like my commands are not working here. Yeah, this happens sometimes with Wayland. So I'll go ahead and just restart here. Let's do system, restart. Let's see. Well, while we wait for that to boot back up, I will continue reading the book in front of me. So the last bullet point was the use of get sockopt and set sockopt system calls to retrieve and modify options affecting the operation of a socket. We also consider a number of other more minor topics and conclude the chapter with a summary of some advanced socket features. Go ahead and get logged in here if I can. Wayland is way messed up. I need to do an update here. Quit out of that. How do I, let's do update. Marchy. I'm getting a lot of errors in my hyperlin config, so I need to fix that. But I'm just going to do a full update of all of Amarchi. Do another restart. Or we'll just reload hyperlin. See if that fixes everything. Alright, hyper CTL reload. Nope. Okay, so let's go under It's complaining about local share Omarchi. Sorry. Get status. Get LGA. We're in an origin dev. Get fetch all. Hey, how's it going? Sorry, Mr. Chat there. I need to get my machine fixed here because it is horribly broken. Hyperlend is broken. I didn't do an update, but I did a restart because some things are broken and then everything broke. And I'm on upstream master, which git show stat. Oh no, this is my... Oh, interesting. I wonder if he merged my commit. What is upstream? Git... Let's do boop, 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 boop. github.com/ yeah, I'll go ahead and unblur my screen here. I feel like that's like super annoying. So I'm getting all these like issues, but what I did notice in the git log is that my commit is head, which seems weird to me that that would be the case. It's saying that it's upstream head. No, I'm stuck on origin dev. I'm curious if you merged my thing though. Let's get GitHub Omarchi. I did have a PR open. I doubt it's been merged though. He's got so many PRs here. Author is Cypher0dev. Yeah, okay. So that means I'm on the wrong commit here. I need to say git checkout master, and then git fast forward, git fetch all, git merge fast forward only with origin master, or upstream master, Okay. Wow, he's got a lot of problems here. Okay. Git log 1. So now I'm on upstream master, and if I cat out .git config, the origin upstream is the Basecamp one. Okay. So everything should be good. Hyperctl reload. Okay, so now I have at least only a handful of errors here. So I'm going to go under, these are probably things I need to fix from my config, which is good. So I go under C0 .config hyper, and then if I open up hyperland.conf, line 13 is some source where I'm sourcing the Omarchi. And it says, hey, globbing error, no match found. Okay, that's weird. If we go back over to, oh, now my themes are all broken. Damn, everything's breaking. Let's do local share Omarchi. Oh no, this is different. So we got a delta here. So let's go under .local share Omarchi, and how are you now? I'm doing good. How are you doing? I'm excited to read this chapter that we have in front of us, which is on advanced socket stuff, advanced topics of sockets. But this machine is broken now, so um, I guess that's part of like working on a rolling release is that your stuff just incrementally breaks. So I could see why people don't prefer prefer to run stable releases instead of rolling releases. Let's try to find a hyperland.conf and then we'll do a delta here. So find iname hyperland.conf. The start menu weren't working out. No, yeah. Yeah, but Windows 11 is supposed to be stable. I feel like Arch, you kind of buy into it not being stable. Let's do a delta between .config, hyperland, and actually I'll do mine. This is mine, and then theirs is config hyperland .conf. Okay, so these are the changes that they made. They removed. If I go under my hyperland.conf, there is this ems thing, config hyper ems. They removed that. Okay, not sure what that's about. And then they also removed window rule workspace 5. It was a commented out thing anyways, so it doesn't matter, but I'll fix it anyways. Match, oops, we say match class QEMU. Okay, so let's go ahead and write that, and then we'll do a delta. Oh, and there's a space here instead of a thing there. Let's go ahead and do the delta again. Okay, no delta. Okay, so it's kind of weird that it says globbing error, error found no match. So that means that there is no config omarchy current theme. That seems weird. Let's cat out config omarchy current theme. Hyperland. Sorry. Config omarchy current theme. Hyperland. Oh, there is no theme. Is there? No, there's no hyperland. Interesting. There's no hyperland file there. So does that exist here? Let's do a find dash iname hyperland.conf. So there is this hyperland under this dude. Themes, sorry, themes, this dude, he has a hyperland.conf. But these other themes, like I was running the, what was it? We'll just do Tokyo Night. They don't have hyperland.conf anymore. Maybe I should do a selection here. So I'll say, hey, I'm going to go to style, theme, and I'm just going to say Everforest. Oh, they got like a preview now. That's kind of cool. We'll run with that one. Okay. Okay, we'll close out of that. Alright, so that fixed some things, but not everything. So config error in hyper input. Okay, so this is actually something I made changes to, so I imagine there'd be a delta. So we'll go back to our delta, and we're going to run hyper input.conf. And we'll do the same thing over here. Input.conf. It's like the Linux meme now. Yeah. I haven't ran Windows in over 20 years, so good luck with that. I'm not a big fan of Windows. So they deleted these things and added these. So they went and they said Alt's toggle instead of Shift's toggle. I don't know what that is. This is something I don't need. I think I added this for my laptop. No, they added this for okay, I added it on my laptop, but then later they came by and added a commented version of it. And then they fixed some stuff here. So I'm just going to roll with the version that they have. So I'm going to say, hey, let's just, instead of worrying about merging them, I'm just going to copy one right over the other. There we go. Hey, did that fix everything? Looks like it did. Can I get my, yeah, look at that. So that wasn't too bad. That's pretty easy to fix. I'm going to go ahead and do another restart just to make sure that everything is kind of fresh. But I think that's all we needed to do. Let's see. Yeah, let me get booted and logged in here. I was actually pretty happy with how little work that was to fix. It gave me all the errors up in like the top of the screen. I then just did manual diffs between the Marchy configuration that was provided and the one that I had locally, and then merged the two. All right. Looks like we're up and running. Bam. Okay, let's get back after this. So if I go under downloads, I think I have the PDF here. Yeah, open the Linux programming interface. And then we'll jump over to the Linux programming interface. What's the last movie I watched? I don't know. It's a good question. I watched the Stranger Things final season. That season really sucked. I can't remember what movie I have seen recently. Yeah. Is there any good movies out that you... But that's like a TV show that I really liked. I feel like a lot of like good stories are now told in serial form instead of like a big theatrical release. I'm trying to think what else. The Expanse, that was like I'm really into sci-fi. So that was like another good show, but that one's a little dated at this point. Oh, there is a glitch on YouTube live streaming right now. Let me see what's going on there. Let's see. YouTube is not receiving enough video to maintain smooth streaming. As such, viewers will experience... Oh, that's not good. I wonder why that is. Nolan movies? Yeah. I like some of his stuff. Some of it's a little too involved. Like the, was it Tenet? That movie is too much to keep it in track in your head. Like the non-linear storytelling, it's definitely like interesting. But you can go too far with it, I feel. Yeah. I think I watched it twice when it came out, and I still didn't understand it fully. So for some reason, YouTube's saying that I have really poor connection right now. No, I don't really watch anime. Saying that I'm getting Yeah, it is really bad. Did it resolve itself? Okay, it resolved itself. I guess, there are some animes that I've watched that I really enjoyed, but they're like from the 90s. Like, I was just talking to my buddy this morning about Ghost in the Shell, the original film. That style of like cyberpunk sci-fi with like atmospheric like vibe, like like cool vibes. Like I feel like that style got lost. Apparently they're making like a new Ghost in the Shell animated series that's like based on the manga, but I'm not really interested in it. I like that 90s style of like 2D animation. And then Akira, of course. But yeah, there's not much outside of that. There's some shows that I watched when I was younger. I'm trying to think what the names were. Oh, Cowboy Bebop, obviously. Like, that was like a really good one. Uh, but yeah, it's hard to get into some of that stuff. It's kind of like, I don't know, not my cup of tea. All right, let's continue reading here now that we're back up and running, and the stream looks like it's doing well. So the first topic here is partial reads and writes on stream sockets. When we first introduced the read and write system calls in Chapter 4, we noted that in some circumstances they may transfer fewer bytes than requested. Such partial transfer can occur when performing I/O on stream sockets. Pretty much like any read and write, you have to assume that it could be a partial read or write, because the kernel could get interrupted. It could, for any reason, it doesn't have to write your data. It could just send you like, a return value that says, hey, I didn't write any data or only wrote partial data. So no difference with when it comes to sockets. We now consider why they can occur and show a pair of functions that transparently handle partial transfers. Oh, that's nice. Read n and write n. That's pretty cool. Because like I've written so many like loops in Go and now in C, where you're just looping and making sure that the write completes. So these, I'm actually interested in these. So yeah. A partial read may occur if there are fewer bytes available in the socket than were requested in the read call. In this case, read simply returns the number of bytes available. This is the same behavior that we saw with pipes and FIFOs in section 4410. A partial write may occur if there is insufficient buffer space to transfer all of the requested bytes, and one of the following is true. A signal handler interrupted the write call after it transfers some of the requested bytes. Yeah, so a signal handler could interrupt it, in which case it would get the error code enter, I think it is. The socket was operating in non-blocking mode, and it was possible to transfer only some of the requested bytes. So then you get E again, I think, as the return on that one. An asynchronous error occurred after only some of the requested bytes had been transferred. By an asynchronous error, we mean that error that occurs asynchronously with respect to the application's use of the call in the sockets API. An asynchronous error can arise, for example, because of a problem with a TCP connection, perhaps resulting in a crash by the peer application. So the peer could have just crashed and went away. In all of the above cases, assuming that there was space to transfer at least one byte, the write is successful and returns the number of bytes that were transferred to the output buffer. If a partial I/O occurs, for example, if a read returns fewer bytes than requested, or a blocked write is interrupted by a signal handler after transferring only part of the requested data, then it is sometimes useful to restart the system call to complete the transfer. In listing 61.1, we provide two functions that do this, read n and write n. The ideas for these functions are drawn from functions of the same name presented in Stevens et al. So that's man knows. Man read n, man write n. So these are not, these are basically functions that he implements in the book here. And that makes sense because I feel like I would have ran into these already instead of writing all these loops myself. So it makes sense that the standard library doesn't provide them. It would be nice if they did, though. So we got our read n, file descriptor, buffer, size count. Same thing with write. So very similar. The read and write n functions take the same arguments as read and write. However, they use a loop to restart these system calls, thus ensuring that the requested number of bytes is always transferred unless the error occurs or end of file is detected on a read. So you still get the same error codes that you would if there's an error, a truly erroneous situation that can't be restarted. So the read, basically we just declare number of bytes fetched by the last read, total number of bytes so far read so far. So each read is going to get assigned into numRead, and then we're going to increment total read by that number. And then a char star buff, which is not buffer, but we copy buffer into buff. That's so that we can do point arithmetic on it here. So we convert the void star into a char star, and then we do point arithmetic to increment by characters. Yeah, exactly. That's what it says here. No point arithmetic on void star. I think you can still do point arithmetic. It does by 1 byte on GCC on Linux, but it's like undefined behavior. Like it's not well defined. So then we go into our loop. We say the total that I read was 0. We'll initialize it to 0. And then we'll loop until total read is greater than or equal to n. So then we do our read on the FD with our buffer. We could pass in buffer here. We don't necessarily need to pass in buff because they're both pointing to the same place. But I guess it makes sense to just use buff from here on out. And then we say n minus total read, and the first read will be 0, so that would just be n. We get the number read. We say, hey, if number read is 0, then we're EOF, and we're just going to return the total read. And then if the number read was negative, then there's some error case. If the error was enter, so it was interrupted by a signal handler, then we want to continue so that we just restart the system call. Else, we're going to return -1 because it's some other error that we can't handle. In the case where it's a positive integer, non-zero positive integer, then we go in and we say, hey, number read, we're just going to increment the total, and then we're going to do point arithmetic on the buffer, so the next read will place the data in the right location. And at the end, we just return the total read, which should equal the n that was given to us. It'd be nice to have an assertion there or something. And then write, it's pretty much the same deal, just in inverse. We're writing instead of reading. So that's kind of handy. I might use those functions at some point just to avoid writing that code, because I've written it in line probably a dozen times now. The shutdown system call. So I have a question about, out of the blue, which CV resume template might work. I don't really have good advice for you for CV resume template. I think just keeping it simple, listing all of your projects that you've worked on, all of your qualifications, all of your experience, prior jobs, and academic background, but keeping it short, because like when someone looks at your resume, they're really just scanning it. And the rule is to have a resume that is 1 page. Like, you don't really want to have more than one page for your resume, even if you've accomplished a lot in your career. Like even now, like when I apply for different roles, like I send a single page resume, because yeah, it doesn't make sense to like overwhelm someone if they're just trying to scan your background to see if you even qualify for the position. The resume, in my experience, doesn't really get you the job at all. It's a filter. So as long as you just have something that's good enough to pass the filter, that's all that really matters. One of the things I've done in the past is just have like little like sliders for my skills. So I would list like all my skills with a little tiny slider, to estimate how far along I am in skill development on that skill. And that's helped. A lot of people have mentioned that in interviews that they like that. But yeah, just spend some time on it. Make sure you spell check it and everything, and you can also give it to people, career counselors. Give it to someone, have them review it. Yeah, it's not really rocket science. The hard work is doing the actual work. Another thing I might recommend to you, if you're not already doing this, is if you search for Brag Doc, Julia Evans. This is a really good thing to do. Of all the things that I work on, and that way, especially when I'm working at a company, it's a good way for your manager to know like all the contributions that you're making. And then when you go for like a promotion or something like that, you have all that information already available. And it's also like just psychologically, it's kind of motivating to maintain a sort of document, outlining all of your accomplishments and everything that you worked on. Yeah. Yeah, if you just Google for like Brag Doc, this is a really good blog post by Julia Evans. She's kind of prolific. Yeah. All right. So we're talking about shutdown system call. So calling close on a socket closes both halves of the bidirectional communication channel. Sometimes it's useful to close one half of the connection so that data can be transmitted in just one direction through the socket. The shutdown system call provides this functionality. So you just give it a socket file descriptor, and then you say which side you want to shut down, read, write, or read, write. Shutdown system call closes one or both channels of a socket FD, depending on the value of how, which is specified in one of the following. Shut RD, which closes the reading half of the connection. Subsequent reads will return end of file. Data can still be written to the socket. After a shut RD on a Unix domain stream socket, the peer application receives a SIG pipe signal and the ePipe error if it makes further attempts to write to the peer socket. As discussed in section 6166, shut read can't be used meaningfully for TCP sockets. Okay, so that's in the future here. We talk about 6163, which is a closer look of TCP state machine and state transition diagram. Okay. So it's mainly used for Unix domain stream sockets. As I've only worked in startup and never had any mention. Sorry, my mouse is covering up half the message here. Never had any mention, had to do or get fired. Mentor, okay. Yeah, my bad. Yeah, it's always important to find mentors where you can. I've had success when I was younger going to meetups. Meetup, that's too many E's in that, meetup.com. If you don't already attend meetups, this is a good website. But there's plenty of other things online that you can go to. And someone can be your mentor and not know it as well. I feel like when I was younger, I had mentors that I interacted with in person that kind of guided me along my early career. But then there's also mentors that I just people I looked up to and learned a lot from. So if you can't find anyone in your local area that can serve that role, it's a big internet. You can find people online, help you along your path. All right, so we're talking about shutdown, right end. Close the right half of the connection. Once a peer application has read all outstanding data, you will see end of file. Subsequent writes to the local socket yield sig pipe, signal, and an e-pipe error. Data written by the peer can still be read from the socket. In other words, this operation allows us to signal end of file to the peer without still being able to read data that the peer sends back to us. The shut write operation is employed by programs such as SSH and RSH. The shut write operation is the most common use of shutdown. It's sometimes referred to as the socket half close. So let's think about that. So we got our sockets bidirectional, and we shut down writing, which says I'm just going to read. And now on the other side, that signals to the writer that it doesn't need to do any more reads. Its reads will return end of file or e-pipe. No, that's if I do writes. It gets EOF on the peer. Okay, that makes sense. And then shut read write closes both read and write halves of the connection. This is the same as performing a shut read followed by a shut write. Aside from the semantics of how argument, shutdown differs from close in another important respect. It closes the socket channels regardless of whether there are other file descriptors referring to the socket. Oh, interesting. In other words, shutdown is performing an operation on the open file description, not the descriptor. Suppose, for example, that socket FD refers to a connected stream socket. If we make the following calls, then connection remains open, and we could still perform I/O on the connection via the file descriptor FD2. However, if we make the following sequence of calls, then both channels of the connection are closed, and I/O can no longer be performed via FD2. So we do a duplicate of socket, and then we shut down socket on both read and write. So FD2 is now useless. A similar scenario holds if a file descriptor for a socket is duplicated during a fork. If either the fork one process does a shut read write on its own copy of the file descriptor, then the other process can no longer perform I/O on its descriptor. Makes sense. Note that shutdown doesn't close the file descriptor even if how is specified as read write. To close the file descriptor, you must additionally call close or exit. Example program listing 61.2 demonstrates the use of shutdown, write operation. This program is a TCP client of the Echo service. We presented a TCP server for the Echo service in section 63. To shorten the implementation, we make use of the functions in the Internet Domain Sockets library shown in 5912. In some Linux distributions, the Echo service is not established by default, and therefore we must enable it before running the program in listing 61.2. Typically, this service is implemented internally by the inetd daemon. And to enable the Echo service, we must edit the file etc inetd to uncomment the two lines corresponding to the UDP and TCP Echo services, and then send sig-hup signal to the inetd daemon. Many distributions supply a more modern xinetd instead of inetd. Consult the xinetd documentation for more information about how to make the equivalent changes under X inetd. We're not going to do that because I don't like inetd. As its single command line argument, the program takes the name of the host on which echo server is running. The client performs a fork, yielding parent and child processes. The client parent writes the contents of standard input into the socket so that it can be read by the echo server, and then the parent detects end of file on standard input and uses shutdown to close the writing half of its socket. This causes the echo server to see end of file, at which point it closes its socket, which causes the client in turn to see end of file. The parent then terminates. The client child reads the echo service's response from the socket and echoes the response on standard output. The child terminates when it sees end of file on the socket. The following shows an example of what we see when running this program. So you're just saying like cat standard input into this file, tell tail heart, and then we just type in some stuff here and end of file it. Then we run the is local CL client, and we say our computer name is Tekapoo, and we shovel in the telltale heart file into its standard in, and then it's basically writes it out to standard out. I really don't see the point of that program, but maybe it's just a contrived example. But let's go ahead and read the code. So you have our main buffer size 100. We declare a socket file descriptor, a place to store how many bytes are read, and a buffer of buff size 100. We then just assert that we have enough arguments. We call inetConnect to get our socket. We then fork. If there's an error, we exit. If it's a client, then we loop forever. If it's a server, we loop forever as well. Client will read into its buffer from the socket that was created up here, and then print out that information to standard out with a period star s. Oh, this is like a regex thing, maybe. Haven't seen that syntax in printf. Not familiar with it. And then once it hits its break, which is where numread is either an error or EOF, then it exits. This should be an underscore exit because it's a child process. I don't know why I did a regular exit. And then the parent goes into an infinite loop. It's doing its reads, but on standard in. And then if it ever is unable to read any data because of an error or EOF, then it goes to shut down stuff. But in this case, it's just going to do write to the socket continually. So it's reading from the file, writing to the socket. So there's going to be some buffering between the parent and the client. So this doesn't have to wait for the client to read necessarily, so long as that buffer doesn't fill up. And then once it's done doing all of its writes, then it calls shutdown on its writes, which says, hey, I'm done. And then it exits. See, this seems like a very convoluted example because the shutdown here, sure, that's going to tell the client you're done writing. Or I guess tell the child that you're done writing. But you can also do that just by exiting. Because when you exit, I guess you can't do it by exiting, because when you exit, your descriptor is closed, but the child itself could continue writing to itself, theoretically. Okay, so it's not so much of a contrived example. This shutdown is actually needed, because if you just exited, the file descriptor would get closed, but because that file descriptor lives on in the client and the client doesn't know it's done reading, it's going to block on its read here. So the shutdown here allows the read here to unblock and allows the child to exit. Okay, that makes sense. In most situations though, you're not like sharing the same socket between both peers. Like you'd create a socket on the client and a socket on a server, and they're completely separate processes, completely separate computers on a network, and you're not sharing the same file descriptor. So when you close on the client when it's a separate process, that actually does send EOF to the reads on the server. So I think while it's necessary for us to shut down in here, I think this example, is dependent on the fact that we have a client and server that are forked from each other, which isn't super realistic. But I mean, it's not too far-fetched that you might want to do that at some point. Okay, 61.3, socket-specific I/O system calls, receive and send. The receive and send system calls perform I/O on connected sockets. They provide socket-specific functionality that is not available with the traditional read and write system calls. So when you receive, you give it the socket file descriptor, the buffer, the size, which is just like a read, but then there's some extra flags that you can specify. Same thing with sending. You just get an extra flags argument. So all the additional functionality is in the flags. The return value and the first three arguments to receive and send are the same as for read and write. The last argument, flags, is a bit mask that modifies the behavior of the I/O operation. For receive, the bits that may be ordered in flags include the following. Before we dive into the flags, I want to man up receive. So that's a standard library thing. It's also a syscall. And then same thing with send. And if we man syscalls RACV, yep, send. All right. Okay, let's go over these flags. So we have the don't wait flag, which performs a non-blocking receive. If no data is available, then instead of blocking, return immediately with the array again. So if you're performing a read on receive and there's no data, it'll just say, hey, try again. We can obtain the same behavior by using FCNTL and setting non-blocking mode on the socket, with the difference that don't wait allows us to control non-blocking behavior on a per call basis, which is nice because when you set the entire socket into non-blocking mode, that's going to affect both reads and writes. Whereas this, you can just say, I just want this specific read to not block. Receive out-of-band data on a socket. So OOB. We briefly described this feature in section 61.13.1, which is later in the chapter. Peak. Receive a copy of the requested bytes from the socket buffer, but don't actually remove them from the buffer. The data can later be reread by another receive or read call. That's interesting. Let's do a little peek. Wait all. Normally, a receive call returns the lesser of the number of bytes requested and the number of bytes actually available in the socket. Specifying message wait all flag causes the system call to block until the length bytes have been received. However, even when this flag is specified, the call may return fewer bytes than requested if a signal is caught, appear on the stream socket terminate the connection, an out-of-band data byte was encountered, the received message from a datagram socket is less than length bytes, or an error occurs on the socket. The wait all flag can be placed the readN function that we shown in listing 61.1, with the difference that our readN function does restart itself by interrupted signal handler. Yeah, I was gonna say that readN seemed more robust because of the signal handlers. All the above flags are specified in SUSV3 except for message don't wait, which is nevertheless available on some other Unix implementations. The message wait all flag was later added to the sockets API and is not present on some older implementations. For send, the bits may be ordered in the flags include the following. Don't wait. More, no signal, and OOB. Out of bounds. Or out of band. So don't wait. Perform a non-blocking send. If the data can't be immediately transferred because the socket send buffer is full, and instead of blocking with the area again, as with receive, the same effect can be achieved by sending the no block flag for the socket. Yep. So if the buffer is full and you're not waiting, that means you need to retry the send. If it is important, obviously. Message more. This flag is used with TCP sockets to achieve the same effect as the TCP cork socket option, with the difference that it provides corking of data on a per call basis. I'm not familiar with that. So we're going to talk about that later in the chapter. Since Linux 2.6, this flag can also be used with datagram sockets, where it has a different meaning. Data transmitted in successive send or send to calls, specifying message more, is packaged into a single datagram that is transmitted only when a further call is made that does not specify this flag. Linux also provides an analogous UDP cork socket option that causes data from successive send or send to calls to be accumulated into a single datagram that is transmitted when cork is disabled. The message more flag has no effect for Unix domain sockets. Interesting. Corking. I mean, I can imagine what that means, but until I read the later section in this chapter, I'm not going to know for sure. But my imagination would be like corking is like you're putting a cork on a bottle and you're filling that bottle up, and then once it's ready, then you uncork it and you send the contents of the bottle. Instead of allowing the contents to get continually flushed out, you kind of allow them to fill up locally first and before you send them. It's kind of like a batching mechanism, I would say. Message no signal. When sending data on a connected stream socket, don't generate a SIG pipe signal if the other end of the connection has been closed. Instead, the send call fails with the error epipe. This is the same behavior as can be obtained by ignoring the no signal flag controls the behavior of a per call on a per call basis. Message OOB, send out of band data on the stream socket, refer to section 61.13.1. Of the above flags, only out of band is specified in SUSV3. SUSV4 adds a specification for no signal. Don't wait is not standardized, but appears on a few other Unix implementations. More is Linux specific. The send and receive manual pages describe further flags that we don't cover here. The send file system call. So this is a performance benefit. If you have a file descriptor for a file and you have a file descriptor for a socket, you want to send that file onto that socket instead of reading data from the file into user space and then writing it to the socket, incurring all the copying and context switching. You can just hand the file descriptors to the kernel and say, you do the copying. So there's less copies and less syscalls. Applications such as web servers and file servers frequently need to transfer the unaltered contents of a disk file through a connected socket. One way to do this would be a loop in the following form. While n is greater than 0, we read from the disk file descriptor into our buffer, and then we write from our buffer into the socket. For many applications, such a loop is perfectly acceptable. However, if we frequently transfer... Since I restarted, I need to fix my locking. Give me 1 second here. What is the use case for Quark? I think it would be for batching. Like if you have a bunch of messages that you want to batch together for performance reasons, like small messages that can fit in a single MTU, then you'd want to send those, you'd want to fill up the MTU first and then send it out as one big batch. Yeah, I implemented batching on a product that I was working on back in 2016, 2017. And it dramatically improved performance. Let me try something out here. Okay, I think that worked. And I need to go to setup or trigger, toggle, idle lock. There we go. And this morning when I went into the gym, I had so much energy, and I came home and I got a bunch of chores done, and I was like, I'm gonna go straight into streaming, high energy, not gonna slow down at all. And then as soon as I started streaming, my brain's just like it's like so sluggish. I don't know what happened. I lost all my energy. All right, what we got going here? Let's restart from this paragraph here. For many applications, such a loop is perfectly acceptable. However, if we frequently transfer large files via sockets, this technique is inefficient. In order to transmit a file, we must use 2 system calls, possibly multiple times within a loop. One to copy the file contents from the kernel buffer cache into user space, and the other to copy the user space buffer back to the kernel space in order to be transmitted via the socket. This scenario is shown in the left-hand side of figure 61.1. Such a 2-step process is wasteful if the application doesn't perform any processing of the file contents before transmitting them. The send file system call is designed to eliminate this inefficiency. When an application calls send file, the file contents are transferred directly to the socket without passing through user space, as shown on the right-hand side of figure 61.1. This referred to as zero copy transfer. Yeah, exactly. So you got disk file, buffer cache, user space, socket send, buffer, network. Lots of copying. Whereas this one just goes directly onto the network as short as possible. Hey Archangel, what's up? Yeah, we're going through some advanced socket programming right now, and we just started on the send file system call, which is basically a system call that allows you to hand the kernel 2 file descriptors, one of them being a file descriptor and the other one being a socket file descriptor. And it does all the copying in the kernel to reduce the amount of copying and syscalls involved. So on the left-hand side here is a traditional way of doing it, where you're copying everything into user space and then writing it back into kernel. Whereas send file allows you to eliminate that copying and syscall context switching. And there's a generic form of syscall, called splice. So this is very similar to send file, but it's more generic. And I don't think they cover splice in this book, so probably won't go into detail on it. All right, let's continue reading. The send file system call transfers bytes from the file referred to by the descriptor in FD to the file referred to by the descriptor out FD. the out FD descriptor must refer to a socket, and the in file descriptor argument must refer to a file to which mmap can be applied. Interesting. Didn't know that that was an additional requirement. In practice, this usually means a regular file. Okay. This somewhat restricts the use of send file. We can use it to pass data from a file to a socket, but not vice versa. And we can't use send file to pass data directly from one socket to another. To do that, you would need splice. So the big use case for send file is like all these web servers that are basically just serving up static files off of the hard drive, off the file system, like CSS and JavaScript and HTML and like all this like CDN type stuff. It's just sitting on the file system, and you need to get it out onto the network as fast as possible. That's like the main use case for send file. Let's see here. Performance benefits could also be obtained if send file could be used to transfer bytes between two regular files. On Linux 2.4 and earlier, outfd could refer to a regular file. Some reworking of the underlying implementation meant that this possibility disappeared in the 2.6 kernel. Some later changes restored this feature in 2.6.3.3. Well, let's pull up the man page, see what the current state of the art is here. Send file. In FD should be a file descriptor open for reading, and out FD should be a descriptor open for writing. Let's see, in FD. The in FD argument must correspond to a file which supports mmap-like operations, so it cannot be a socket itself. Except since Linux 5.12, and if out FD is a pipe, in which case send file desugars to a splice, and its restrictions apply. So basically, send file has now become overlay of the splice syscall. I didn't know that. So I guess, like, depending on your use case, you should just roll with send file, because splice is a little bit more complicated of an API. Send file is just like, you got two file descriptors, you got the offset, and the amount of bytes that you want to copy. It's super simple, and it returns the amount of bytes that were copied. Whereas man to splice, this one's a little bit more involved. You have offsets for both in and out. You have the size that you want to copy. You have flags, and there's some restrictions around the one of the file descriptors needs to be a pipe. So I would just use send file until it doesn't work for you, and then use splice. I know the Go networking standard library, when you give it two sockets, it uses splice. I do not know if you give it a file in a socket, if it uses send file. That's kind of like an experiment I might want to run. Why don't we do that now? So let's go into chapter 61. And I got a makefile. Can this thing do Go files? It cannot. So let's find a makefile that can do Go files. I'm just going to do a find for any Go files, because we had some Go files here before. So I'm going to say chapter 56. Its makefile probably has Go support. Yeah, there we go. So let's go ahead and copy that into chapter 61 and cd into chapter 61. We'll just run make. It's not going to do anything. We'll open up our sendfile.go, and we're just going to do package main, and we're going to do a main func. It's been a while since I wrote any Go. So we're going to need to open a FD for this source code, say. because that's a file we're guaranteed to have. Or not guaranteed, but it's very likely that we'll have the source code here. And then we're going to open a socket to actually, you know what we're going to do? We're going to start a TCP server that writes the content to each client using IO copy. So that's pretty much the game plan here. We're going to need a func that says handle connection, handle con. It's going to take a con, which is pointed to net.con. And here, just go ahead and write that to get our imports. So here we're going to say io.copy from or to the con from our file or we'll just say file. So we don't have file, so we're going to need to pass that in as well. And the reason why I did this as a separate function, named function, is because it's going to be running in a Go routine. So here we'll have our file, which is a pointer to file.file, maybe? I don't know. I don't actually know what the type is. We're going to have to figure that out here. So let's do that by opening here. It's been a while since I've done any Go, but let's just search for Golang open file OS. So we got a, let's make this a little bit bigger here because I'm not getting the, there we go, the index. So we got an open somewhere, right? Element OP, I don't see it. Open. Here it is. So this is an OS file, not a file.file. That's where I messed up. So we say OS file. And then up here, we're going to say os.open. And we're just going to say the source code, which is sendfile.go. So os open gives us back a file and an error. So we'll say file, error, and we're just gonna, we'll say func panic error, takes in an error, and it just says if error is not equal to null, we're going to, not equal to nil, sorry. Then we're going to panic on the error, I think that's how you do it. Okay, so now in here we can say, hey, panic error of error. So it's kind of like an assert. Let's go ahead and make this a little bit better here. So we got a typo here. Declared not used, that's fine. So now we're going to say net.listen. And we give it network and address. Network will be TCP. The address will be colon, I think I can say 0.0.0.0 and then just say colon. I wonder if I can just do colon here. We'll see. So that'll give us back a listener. I think it'll give us back an error as well. Yeah. So we say listener error. And we'll do our panic error on that. And then we go into a for loop here, forever, where we say listener.accept the connection. So that's going to give us back an error and a con. So we say, okay, con error. We're going to panic on that error. And then we're going to spin up a Go routine for handle con, giving it the con in the file, and that needs to be spelled right, and I think that's it on that. This thing I need to fix because of the types, maybe. It's a netcon, yeah, a pointer. Oh, it's it. So it's not a pointer because this is an interface. Netcon is an interface. Okay. And then this, we can just assign the error if it occurs, because I think IO copy gives back an error, right? Okay, sorry, my typing is not great here. Okay, so written an error. So we get back n and error. And we'll say if error is not equal to nil, instead of panicking, since we're handling an individual connection here, I'm just going to say log.print or printf, and we'll print out error occurred when copying %s or v. I think we do v error here. Otherwise, we'll just print out, or we'll just leave it without any message there. No news is good news. Cool. So that's pretty much the entire program. You can delete these comments now. The reason why I like Go is that you can just like type it out yourself. It's not so like complicated that you can keep everything in your head. Whereas with C, you always have to be referencing man pages. I mean, I guess it did reference a little bit of documentation here, so that's maybe not fair, but for the most part, you can keep most of it in your head. Between your knowledge that you keep in your head of the language and the LSP, like you shouldn't really have to use documentation too much. So another thing I want to add here, so this is an infinite loop doing its listening. So I'm just gonna, before we enter the infinite loop, I'm gonna say we say log.printf, and we'll say here listening on %s, and we'll give it this variable adder or constant adder that we have not. Actually, you know what? We should probably use listener.adder. So I think that has a string representation. So let's go ahead and run that. Make, build, send file. Okay. So that worked. So now we go launch a client here. I'm just going to use curl maybe. Would curl work here? No, because it's going to assume HTTP on the response. So I'll just do a netcat localhost 45331. And hey, we got our source code up. So I did all that so that we could trace this. And we could see exactly what syscalls it's making, if it's doing a splice or if it's doing a send file. So let's go ahead and do our connection again. And oh, the port number changed. That's why that failed. So I need to get my port number again, which is way up here. So many syscalls that Go runtime does. So the port got lost somewhere in here. All right. Let's see if we can find the port. Where would that have been printed? There's so many syscalls it makes. It's crazy. All right, well, I didn't see that port number outputted. Here it is. Listening on this right here. It got output after the output of strace. That's why I didn't see it. All right, let's try netcatting it again. I'm going to put some new lines here just to space off from that. Okay, so it actually did use send file. It didn't use splice. So what I've observed here is that when Go is sending a file to a netcon, an OS file to a net.con, which is basically a file descriptor to a socket file descriptor, it'll use send file. If it's sending one socket file descriptor to another, then it will use splice, which makes sense. So that pretty much follows like my recommendation earlier, which is to use send file until you can't use it, and then fall back onto using splice. Cool. That was a fun little exercise. Let's go ahead and kill this. And I'll kill this terminal as well. We'll clear the screen. All right. We didn't answer the question on whether you can use regular files. Let's try doing a test there. We'll say vim send file. Actually, no, I'm not going to do a go test on that because I feel like that would be a little bit strange because Go's runtime might implement it any number of ways. So what we really want to do is do a send file.c, but because my build directory would get confused, I'm going to say send file between files, send file, send two files. Maybe we'll do it like this. Okay, and then in here, just gonna create a main. We'll pound include, oops, our standard lib.h. We're gonna need our man pages for a send file. So that's gonna require send file.h. And oops, didn't get the copy there. There we go. Then in here, we're going to open file A, open file B for writing, reading, and then we're going to send file between from A to B, and then assert contents were transferred. Okay, so in here, I'm going to just say assert, so we're going to need assert.h. Assert that argc is equal to 3. And then we are going to then say file path, we're going to say char star file path A, and we'll do this path A is equal to arg c of 1, and we'll say file path B arg c of 2. We're also going to assert that file path A strlen of file path A is greater than 0. And same thing with file path B. And if I do a man on strlen, I think that's just the length of the string, right? Yeah. Nothing weird. Nothing weird about that. It says it excludes the terminating null byte, which is what you'd expect. So let's go back to send file man. Okay, so now we have, what is this saying? Subscripted value is not an array, pointer, or vector. Oh, sorry, these are argv, not argc. My bad. And then call to undeclared library strlen. Where's strlen? String.h, that makes sense. Okay. All right, so now we get our file paths. We can do our opens. I'll probably need fcntl for this, right? Man to open. Yeah, fcntl. fcntl.h. We're going to open our file path A. The flags, we're going to say, since this is read only, we'll say O read only. And we're not going to create it. because we'll create these out of band, and then we'll leave the mode off because we're not going to create it. So that'll give us int, which will be our a or FDA, and we need to assert. We'll do this for both, and then we'll do asserts. So file path B, we're going to do our write only, and then we're going to assert that FDA is greater than or equal to 3. And same thing with B. So now we got some legit file descriptors here. We can then call our send file. So let's go back to our man page for send file. In fact, you know, I've seen a lot of stuff is using openat now, which I think the difference is that you give it a dirfd, but I think I'm just going to roll with open. Okay. So let's go to send file. We just say, hey, send file to FDB from FDA. Offset is 0. Size is, so we're going to need to stat the FDA as well to get the size. So let's go to man2stat. And we're going to grab sysstat here. And we're going to say stat of the path. No, we want fstat because we have the file descriptor already. So we give it FDA. Oops. Actually, you know what? I'm going to see if send file requires that argument or if I'm just doing this work for no reason. So if you look for count, look for count here. Count is number of bytes to be copied within the file descriptors. Okay. It doesn't say anything about it being optional. So I'll just assume that we need to do this. Let's go to stat again. So fstat, we need our stat buff. So we're going to say SB is a struct stat pointer? No, just struct stat. And we're going to initialize that to zeros, all zeros. Actually, you know what? We don't need to do that. Just extra work that we don't need to do. So fstat, we then pass in a reference to our stat buffer. And that gives us back some result. And then we're going to assert that result. So if we look for return here, on success 0 is returned. So assert that result is equal to 0. Okay. So now we can say stat buff, and then we say dot. Was it len? I think it's len or size. Size, yeah. st size. Okay, that's all of the arguments for send file. If we go back here, it gives us back the number. So this, I'll say a signed size tn is equal to send file. And then if I look for a return here, it's going to say on error -1 is returned. So I'm going to say assert that n is greater than or equal to 0. And then we can exit success. Cool. So we got our little program here. We'll go ahead and close this out. We'll go ahead and make that up. So we need to create our 2 files. So I'm just say vim up temp a. This is going to be ASDF hello world. This is an example of send file between 2 files. And then I'm going to touch temp B. If I cat that out, there's nothing there. But if I cat out temp A, it has all that stuff in it. So now I'm going to run my build send 2 files temp A to temp B. No errors, and if I cat out temp B, it has everything now. And if I cat out temp A, it has everything as well. So we demonstrated it worked. That wasn't really what we were getting at, though. Actually, that is what we were getting at. We gave it 2 file descriptors for files, and it works. So send file can work between a file going out to a socket, or it works between 2 different files. But it seems like it might not work between 2 sockets, which is where you need the splice. Cool. All right, let's move on here. So if offset is not null, then it should point to an off-t value that specifies a starting file offset from which bytes should be transferred from infd. This is a value result argument. On return, it contains the offset of the next byte followed by the last byte that was transferred from infd. In this case, send file doesn't change the file offset for infd. The offset is null, then bytes are transferred from infd starting from the current file offset, and the file offset is updated to reflect the number of bytes transferred. All right. The count argument specifies the number of bytes to be transferred. If end of file is encountered before count bytes are transferred, only the available bytes are transferred. On success, send file returns the number of bytes actually transferred. Subset 3 doesn't specify send file. Versions of send file are available on some other Unix implementations, but the argument list is typically different from the version on Linux. Starting with kernel 2617, Linux provides 3 new non-standard system calls, splice, VM splice, and T, that provide a superset of the functionality of send file. See the manual pages for details. So if we man up splice, I didn't notice that because it's not in this man page. There's this thing called VM splice, man to VM splice. Interesting. Splice user pages to from a pipe. This one I have not encountered. I feel like I can spend like an entire day just going into details of like splice and VM splice here and like playing with them. But that's not what I really want to do today. Splice user pages to from a pipe. Okay. So I imagine the VM is for virtual memory. It takes in a file descriptor and an IO vect, which is not documented in this man page. NR segments, not sure what that is, and flags. If FD is open for writing, VM splice system call maps segment ranges of user memory described in IOV into a pipe. If FD is open for reading, fills the ranges of user memory described from a pipe. So FD has to be a pipe. File descriptor FD must refer to a pipe, yeah. The pointer IOV points to an array of IOVEC structures that are described in IOVEC. IOVEC3 type. The flags argument is a bit mask that's composed, I don't care about. So it basically allows you to like take virtual memory range and write it to a pipe, or take a pipe that's open for reading and write it to your virtual memory. So what I'm picking up here is that this is kind of like the way that you introduce the user's virtual memory address space into a normal splice pipeline, because the regular splice syscall uses pipes as well. So it seems like you would say you wanted to send some of your memory out to a socket using splice. The first thing you would do is splice using VM splice a bit of your virtual memory into a pipe that's open for writing. And then you take that pipe and then you would put it onto a normal splice syscall that is then configured to read from the pipe and write to the socket. And it might seem like a bunch of steps there because there's 2 syscalls now. There's a VM splice and a regular splice. But my guess is that that would be more performant than doing, in certain situations, than doing all the reading and writing itself, because you're not copying. I guess you are still copying. I don't know. I'd be curious if there's more copying involved between this and a normal write syscalls. There's certainly more opportunity to save on syscalls themselves, because write, if you have like say like 2 gigabytes of like data in RAM you want to write out to a socket, that's going to be a lot of write syscalls. Like, I guess theoretically you could possibly reduce the amount of write syscalls by making your buffer size really big. But typically it's going to be a lot of smaller sized write syscalls. Whereas a splice, you can just say, hey, this is all the memory I want you to write to this pipe. Just go ahead and do it. And then the kernel takes care of it. Cool. I didn't know about VM splice. I learned about that. I'm going to highlight that in the book here because I think that's interesting. And then there's this thing called T. It's just called T. I'm familiar with T on the command line, but this is duplicating pipe content. T. T duplicates up to size bytes of data from the pipe referred to by the file descriptor in to the pipe referred to by the file descriptor out. It does not consume the data that is duplicated from in. Therefore, the data can be copied by a subsequent splice. So it's kind of like a peek type thing. So you're copying from in to out, but in a way that is not going to change the cursor of where the data is in the pipe. Okay. And all right, some examples there. Cool, let's continue reading. All right, we're back to the cork option. Nurnath, you're asking about corking before. So this is about corking here. The TCP cork socket option. To further improve the efficiency of TCP applications using send file, it is sometimes useful to employ the Linux-specific TCP cork socket option. As an example, consider a web server delivering a page in response to a request by a web browser. The web server's response consists of 2 parts: HTTP headers, perhaps output using write, followed by the page data, perhaps output using send file. In this scenario, normally 2 TCP segments are transmitted. The headers are sent in the first rather small segment, and then the page data is sent in the second segment. This is an inefficient use of network bandwidth. It probably also creates unnecessary work for both the sending and receiving TCP, since in many cases the HTTP headers and the page content would be small enough to fit inside a single TCP segment. The TCP cork option is designed to address this inefficiency. When the TCP cork option is enabled, on a TCP socket, all subsequent output is buffered into a single TCP segment until either the upper limit on the size of the segment is reached, the TCP cork option is disabled, the socket is closed, or a maximum of 200 milliseconds passes from the time that the first cork byte is written. The timeout ensures that the cork data is transmitted if the application forgets to disable TCP cork option. We enable and disable the TCP cork option using the sock opt system call. The following code, which omits error checking, demonstrates the use of TCP cork on our hypothetical HTTP server example. So the idea is that your web server is emitting the header section of the response, and then the rest is like the file data that you're sending using send file. And instead of sending them as 2 separate TCP segments, you just tell the kernel, hey, I'm going to be writing a bunch of stuff. It's not going to take more than 200 milliseconds to me to fill up this segment. I'm going to do all these writes. Hold on until I'm done and then send everything, instead of doing separate network transmissions for the different TCP segments. Okay, so he's got some example code here we can review. So opt val is an integer, enable TCP cork option on socket FD. Subsequent TCP output is corked until this option is disabled. So set it to 1, and then set suck opt, socket FD, TCP, cork, option, and the size of opt val, which is just the size of the int. So TCP cork He forgot a semicolon here. This code is not carefully read here. I'm confused how this size of opt val actually writes the 1. If we man up set sock opt, sorry, typo. Okay, we look for cork. It doesn't even seem like cork is an option here. Maybe they're documented in another document. Maybe there's socket options, man socket, cork. Nope. All right, this is a standard library. If we do this one, maybe cork. Nope. Ioctal socket 2. Okay. Man 2 ioctal. Cork. Yeah, it doesn't seem right. Socket. Cork. No. I don't know where this is documented. But if we just look at man 2 set sock opt. So it takes in the length. That's not right. He must be calling a standard library set sock opt. Yeah, he's calling the standard library version. So it takes in the socket, the level, the option name, and then a pointer to the value itself. He's missing the pointer here. I think this code wasn't really code reviewed. Yeah, so in my book, the text actually has an extra argument here, which is ampersand opt val. Because he's not passing in the actual value, he's passing in the size of the value. So there's an extra argument here that's missing. And then the book still doesn't have a semicolon here either. Let's see if he has that in the errata yet, because it's missing a semicolon there. It's a small thing, but we found one errata so far, so it would be cool to get another one. So the Linux programming interface errata. And this is page 1262, which is far, far down here. Let me zoom out a little bit here. 1262. It's been quite a journey reading this book. I'm surprised like he had an errata that in a fix for that, but he didn't catch the semicolon. 1262. Yeah, this is the opt val that I mentioned, but he doesn't have the semicolon here. I mean, this won't compile, right? I mean, let's try it. Let's grab his code here. Let's take it over to a terminal. We'll say errata test.c. Paste it in. Oops. Let's do a main here, and then we'll copy it again because I didn't copy it right. Okay. Paste it in. Yeah, see, he doesn't have the... Delete all these things that are not needed. He needs that semicolon. And then up here he needs the ampersand opt val. Email him, bro. I have one other errata that I've caught so far. It's because this is like pseudocode. He hasn't really like ran this code. It's always like a hazard when you're writing code in a book like this, where it's obviously not intended to be compiled, like this, the ... stuff, like that's not C. So he obviously didn't intend for this to be taken literally here, but because we're pedants, we're going to take them literally. So the read and write will be, actually I don't even know, man read. Man to read is Unix standard. Unix standard.h give us those. The set socket op. Set sock opt is socket.h. Sys socket.h. And then what else we got here? Send file, which is going to be syssendfile.h. And then what else we got? Standard lib, because of the exit success. Okay, that should take care of it. It says IP proto TCP. We're going to need to grab that. So I wonder where that's defined at. What header is defined in this guy here. And then TCP cork. Okay. Wait a minute. Oh. This needs to be TCP.h. There we go. So now we got to create our socket. So we call socket domain type protocol. So domain is going to be I forget the actual symbols here. Man to socket. Domain is AF inet, yeah, AF inet. The type is going to be a stream, which is sock stream. Oh. And then the protocol, I think that's just like null. I think you just do 0 on that. 0. This will be sock fd, and it has type int. Okay. And then our write, man to write. So takes in the file descriptor, a buffer, and the size t. I'm just gonna comment these out because they're not even valid C code. So if you remove the semicolon here, it's a compiler error. So that's all I wanted to demonstrate there. So errata test, semicolon, errata, semicolon is needed here. Okie dokie. Next page. All right. We could avoid the possibility of two segments being transmitted by building a single data buffer within our application and then transmitting that buffer within a single write. Alternatively, we could use write v to combine two distinct buffers in a single output operation. However, if we want to combine the zero copy efficiency of send file with the ability to include a header as part of the first segment of transmitted file data, then we need to use TCP cork. What's cool is like I didn't know about this. This corking option. I wrote something that did exactly this using splice though instead of send file, and I didn't use TCP cork. So I left some performance on the table there. So yeah, this whole corking thing is like something I was not aware of. All right. In section 61.3, we noted that the message more flag provides similar functionality to TCP cork, but on a per system call basis. This is not necessarily an advantage. It's possible to set the TCP cork option on the socket and then exec a program that performs output on the inherited file descriptor without being aware of the TCP cork option. By contrast, the use of message more requires explicit changes to the source code of a program. FreeBSD provides an option similar to TCP cork in the form of TCP no push. Retrieving socket addresses. The get sock name and get peer name system calls return respectively the local address to which a socket is bound and the address of the peer socket to which the local socket is connected. So it'd have to be a connection socket. It can't be like a listening binding socket. Makes sense. For both calls, sockfd is a file descriptor referring to a socket, and adder is a pointer to a suitably sized buffer that is used to return a structure containing the socket address. The size and type of this structure depend on the socket domain. The adder len argument is a value result argument. Before the call, it should be initialized to length of the buffer pointed to by adder. On return, it contains the number of bytes actually written to the buffer. The getSockName function returns the socket address family and the address of which the socket is bound. This is useful if a socket was bound to another program, by another program, e.g. inetd, and the socket file descriptor was then preserved across an exec. Or if you like bound it using like the all zeros address and you want to know, or the all zero port, and you want to know which port it acquired. Kind of like we did in our Go test here. Like this send file.go. So I call listener adder to get the address that it listened on because I didn't specify up front what that was. So if we run strace again on that, so this is where it like printed out that message. It said listening. But I'm wondering where it actually read that. So 36177. Here it is. Get sock name. So this is exactly what the book is talking about. There's a syscall made here. Get socket name. And this is the result, the second argument. So this is the actual result from here to here. So you can see how it got the port. That's one of the things I like about strace is it does a really good job at like showing you a human readable format. So instead of showing you the IPv6 port number in big endian, it actually uses the conversion function to convert it into little endian, so you can see it as it would be represented in like a normal decimal representation. And then it wraps that number in a function that would need to be applied to it to convert it back to big endian. It's pretty cool. I like that they do all this. strace is like, I mean, it can be intimidating, it can be overwhelming, but it is pretty solid. Not gonna lie. Cool. So that's it, doing that call right there. Calling getSocketName is also useful when we want to determine at the ephemeral port. So that is exactly the use case that I used it for just then in the Go code. Number that the kernel assigned of a socket when performing an implicit bind of an internet domain socket. The kernel performs an implicit bind in the following circumstances. After a connect or listen call on a TCP socket that has not previously been bound to an address by bind, on the first send to of a UDP socket that had not previously been bound to an address, or after a bind call where the port number was specified as 0. That's the situation we're in. In this case, the bind specifies an IP address for a socket, but the kernel selects an ephemeral port number. We actually specify 0 for both the port and the address. And if we want to see that, you can see the bind up here. The port was 0. And where's the adder? This is V6 port was 0. Flow info was 0 as well. iNet P to N. Okay, so this is something that Go runtime injected in here, which is IPv6 localhost or all interface address. Let's see, the get peer name. This next page, get peer name system call returns the address of a peer socket on a stream socket connection. This is useful primarily with TCP sockets if the server wants to find out the address of the client that has made a connection. This information could also be obtained when the accept call is performed. However, if the server was exec'd by a program that did the accept, e.g. inetd, then it inherits the socket file descriptor, but the address information returned by accept is no longer available. Listing 61.3 demonstrates the use of getSockName and getPureName. This program employs the functions that we defined in listing 59.9 on page 1228 and performs the following steps. Use our inetListen function to create a listening socket, listenFD. Okay, I'm not going to read through all of this because it's pretty basic stuff, just showing how to use those two system calls, which we already are pretty familiar with. A closer look at TCP. So how long do they go on this TCP closer look? So they got plenty of diagrams coming up here. And it's about, let's see, 66 to 74. So that's about 8 pages roughly of additional TCP. And then we talk about some of the command line tools, some of the socket options, inheritance flags, TCP versus UDP, advanced features, out-of-bound data, passing file descriptors. I think you have to have Unix domain sockets. I don't think TCP sockets support that. Receiving sender credentials, sequence, yeah, all this stuff. This cool stuff. All right. A closer look at TCP. So he's going to spend 8 pages here roughly going over some of the edge cases of TCP. Which is, I think, it's going to be helpful for me because while I have done a lot of like socket-like programming in Go, and I know roughly some of the states in the state machine for TCP, I don't actually know it to a great detail. Like I know the TCP handshake with like synac act and then reset on close of the file descriptor. You reset the connection, but there's always like states in between that I'm always kind of like not too sure about. I have to reference documentation for. So hopefully get into some of that here. Knowing some of the details of the operation of TCP helps us debug applications that use TCP sockets and in some cases to make such applications more efficient. In the following sections, we look at the format of TCP segments, the TCP acknowledgement scheme, the TCP state machine, TCP connection establishment and termination, and the TCP time wait state. So it is almost noon here, and I've been going for an hour and a half. I think I might break here for lunch. I'll go for another 5 minutes roughly, but I think I'm going to break here for lunch soon, and then take my lunch break and go for a run. I'm going to get some cardio in, and then come back and finish the rest of this chapter. So after this afternoon, we will be entirely done with sockets, and we'll be moving on to terminals, pseudo terminals, and some of the more advanced I/O features. But yeah, let me just finish up reading a couple pages here, and then we'll take a break. All right, format of a TCP segment. So figure 61.2 shows the format of a TCP segment, of the TCP segments that are exchanged between the endpoints of a TCP connection. The meaning of these fields are as follows. Source port number, this is the port number of the sending TCP. Destination port number, this is port number of the destination TCP. Sequence number, this is the sequence number of the segment. This is the offset of the first byte of data in this segment within the stream of data being transmitted in this direction over the connection, as described in section 5863. Okay, so if you're transmitting 8 bytes, then, and say your sequence number is 0, then the next sequence number for the next segment, TCP segment, will be 8, because you sent 8 bytes in the previous segment. I think that's probably how they enable packet fragmentation then, because if you have a single TCP segment that's larger than an MTU, then at some point that segment is going to need to be split. It's going to be fragmented into multiple packets. And when they do that, they can just modify these sequence numbers because the sequence number is based on the size of the segment. What are you going to have for lunch? I don't know yet. I need to possibly go to the grocery store and get food because I haven't really been keeping up on my grocery shopping. I do have some chicken thighs left in the fridge, so I might just eat those for lunch. Yeah, I might just do that, yeah. Okay, so let's just look at this segment real fast, and then we'll take a break. So source port number, destination port numbers. TCP and UDP alike are both transport protocols, and so they're transporting data, and they need to address the port number on both the host and destination. Sequence number we just kind of described. It's for reassembling these TCP segments at the destination. It also plays a role in packet fragmentation. Acknowledgement number, this is like when the client is acknowledging the data being sent, or I guess in both directions, bidirectional. So when the receiver of the packets acknowledges that it received a segment, it'll send an acknowledgement for that sequence number. And then there's header length, 4 bits, reserve 4 bits, control 8 bits, window size, TCP checksum, urgent pointer, options take up 40 bytes. Interesting, that's a lot of data. So all of that is the header. And then the data is just, however many bytes remain. So the important thing to see here is that TCP has checksumming built into it. The application itself should also be doing data integrity work because this isn't foolproof, but it does allow a lot of the errors to get detected at a lower level than the application has to worry about. So retransmissions can be handled on the TCP level. Yeah, cool. So we'll take a break here, and we'll come back to this in about, I'm giving myself about 2 hours, so probably around 2 p.m. my time. I'm gonna hop back on. Cool. All right. Hope you learned something. I certainly did. It sounds like the corking stuff you might have enjoyed learning about. But yeah, I'll be back in a couple hours here, and we're going to dive more into some of the details of TCP. Cool.